So in this video I wanted to just make a quick comment on how you can implement the numerical algorithm to solve the differential equation we've been talking about. So this is the differential equation that describes the evolution of a neuron's membrane potential. And in a previous video I derived this method for solving this differential equation. And specifically what this is telling you is that you are going to be taking small steps in time, and delta t tells you how small that step is. And the voltage at the next time step, at the n+1 time step, can be approximated based on what you know the voltage to be at the previous time step, and your calculation of what the steady-state membrane potential is. And I've posted some code, and I've given a little snippet here below. I just wanted to very quickly go over this for, maybe people who haven't had as much programming experience. Like if you know Python, you can probably look at the code in its entirety and figure it out. But for those of you who haven't seen a lot of, or haven't coded, I just wanted to go over this very simple part of the code because it is so simple and it shows exactly how you can implement this numerical method. So essentially what I've defined here is sort of a routine or function that takes three variables. So if you give this piece of code the injected current that you're injecting into the cell, the resistance of the cell, and t, which is just keeping track of the time of the simulation, then it will solve for the membrane potential of the cell and basically spit it out for you. So that's what this return statement here basically it's a self-contained bit of code that you say, okay, if I specify my inputs into the cell and the parameters of the cell, can you solve for me the membrane potential? And that's what this bit of code does, and it's just a very simple bit of code that is implementing this routine up here. So let's go through it sort of step by step. So ij is a list of numbers. So I'll have like a square bracket, and it basically tells the amount of injected current at time point 1, the amount of injected current at time point 2, the amount of injected current at time point 3, etc., all the way up to, let's say there's capital N time points. So that's what the injected current, that's how it's represented in this code. Similarly, the t is the time at time point 1, the time at time point 2, all the way up to t of n. So t of n is sort of the maximal, or the length of the simulation that we're running. And at each time point, you specify what the amount of current you're injecting to the cell at that time point is. And the last input into this function is R, which is just the resistance. That's just a single number, because we're assuming that the input resistance is constant over this simulation. Then the next few lines of code, I'm just saying, well, this is, I'm defining what the resting membrane potential is, so I've been calling that E, and negative 60 millivolts is a reasonable resting membrane potential. Then I defined the capacitance of the cell, and I decided to, let R be a free parameter, but just for simplicity's sake, I've just been keeping the capacitance of the cell equal to 1. This next line of code is perhaps a little bit difficult to understand, but this is basically just constructing a list of zeros. So I'm creating a vector for the voltage, and this eventually will hold the voltage at time point 1, or the membrane potential at time point 1, 2, 3, all the way up to the voltage at n. So for now, I'm just filling it full of zeros because I haven't solved the equation yet. But I'm going to use this numerical method to actually fill up this vector. So that's what that line of code is doing. Now I'm setting my initial condition in this next one. I'm saying the first element in this list of membrane potentials, or V. So you can think of V as a list, or the more technical term is an array. And I'm saying the first element of this list of numbers is going to be equal to the resting membrane potential. So that's just an initial condition that I'm imposing on the system. And then the next line of code is just calculating what the time constant is. So remember, we're assuming that the resistance is constant. We're also assuming that the capacitance is constant. So the time constant in the membrane is R times C, and that corresponds to this term up in the original differential equation, if that wasn't clear. So then I do what's called a for loop. And the for loop is basically saying I'm going to repeat these next two lines of code a lot of times. And if you just look up any programming language, for loop is one of the first things that you'll learn in Computer Science 101. And essentially, all that this is doing is saying, okay, I'm going to start at the first time step, so V1, or my initial condition, and then from V1 I'm going to approximate what V2 is, the membrane potential in the next time step. And then once I know V2, then I'm going to repeat this same line of code to approximate V3. And I'm going to keep doing this all the way up until I run out of spaces. And that's what this first line of the for loop is saying. I'm going to take a variable I, and I'm going to run it through a range of parameters. And essentially, I'm going to start at I equals, in this case, 0, because 0 is the first element in the Python programming language. And so I'm going to start at the first element, and then I'm going to move to the second, and then I'm going to move to the third, and then I'm going to go all the way to the end. That's what that line of code is saying in a nutshell. And for each element in this array, how am I going to estimate the membrane potential at the next time point? Well, first thing I'm going to do is calculate the steady state membrane potential, and we've already shown before that VSS equals E plus IR. I've shown that in a previous video. And remember that I is changing at each time point, so at each time point I'm updating what my injected current is, because remember, I and J is also just a list of numbers, so I'm taking the ith number in that list. So for each element in these arrays, then I'm estimating what the steady state voltage is, and then once I have the steady state voltage for that particular number, I'm just going to estimate what my membrane potential is in the next time step, so the I plus 1 time step, and that's equal to VSS minus V of I times exponent of this. So this line here, I'll just erase this to make it clear. This line right here is exactly equal to this. And I'm using I rather than N here, but other than that, it's pretty much the same. And the other difference, I guess, is I'm using the difference in time between the ith and the ith plus 1 time step. I could have just made a parameter called delta t or something, but so this is just the time difference, which is what this corresponds to up here. And other than that, this this exp function is defined to be e to the exponent of this. So this line of code is exactly the same as what I wrote before, and essentially we're just going to keep on calculating the steady state voltage, and then based on that steady state voltage, calculate what the voltage or the membrane potential will be in the next time step. And we're going to do that until we reach the end of the list. So len v is the length of that list I was talking about. So that's the iterative method there. And if if you already know some programming, this should be relatively simple for you. And if you don't, hopefully this gives you at least some intuition about how you actually go about solving this numerically. And hopefully, even if you didn't understand this completely, you can probably at least understand that this is a relatively simple algorithm to solve for what the membrane potential is. And if you look up for loops and functions, and you can learn Python or any other programming language, you should be able to implement this routine pretty quickly. So this is the heart of the program and the code that I put up. I'm not showing the entire program because a lot of it's sort of extraneous and not really relevant to what we were talking about. But I wanted to talk about this explicitly so that those of you who were interested would get a more concrete understanding of how to numerically solve for the membrane potential. Okay,